Train spotting. The act or practice of observing trains, particularly as a hobby, with the aim of noting distinctive characteristics and features. Or, in slang, it means the act of being obsessed with any one trivial topic. Or, from the movie Trainspotting, released in 1997, the act of shooting up heroin. In this video, we'll try perfect spotting, the act or practice of observing for and obsessing with small details for the purpose of distinguishing the matchmaking algorithm used for one given individual record of games. Guess which algorithms made these group of records? Can you tell just by looking? Here are the answers. You might have been able to get this one right, as the black and white lines just look longer to the naked eye. But what about the rest? Even with only 10 samples each, they look so similar. For this, we'll use neural networks, the classifying kind. We will start with a simple basic model named First Basic NN, and gradually make our NN classifier more complex to better accommodate our findings and needs. First Basic NN has 3 layers, with one hidden layer in the middle, and the ReLU activation function was used. The image, or a series of 300 ones and zeros, will be fed into the input layer. The purpose of the First Basic NN is to distinguish which one of the 3 matchmaking algorithms was used for a record, hence the 3 nodes in the output layer. Here's how the First Basic NN performed, trained for different epochs. Wait, but what are these? And how should we understand them? According to sources, sensitivity is the probability of detection or hit rate, and can be written as TP over P, number of true positives over number of actual positives. Precision is the ratio of true positives out of all positive predictions, and can be written as TP over PP, number of true positives over number of positive predictions. But this sounds confusing. How should we interpret them? Given this table, what is usually called a confusion matrix, suppose 2 different scenarios for 2 examples. A. We know which algorithm made the record and just want to test the model works regarding perfect MM. B. We don't know which algorithm made the record and want the model to tell us the answer and assess its performance regarding near perfect MM. In scenario A, where we already know the answers, if we wanted to know if our model was identifying perfect MM images correctly, we start from the observe section and follow this arrow for the label we want to see the success rate. In scenario B, where we don't know the answers, if we wanted the model to identify the algorithm for an image and wanted to assess its performance regarding near perfect MM classification, we start from the predictions axis and follow this arrow for the label we want to see the success rate. In other words, sensitivity means know first, predict later, and is for scenario A. Precision means predict first and know later, and is for scenario B. With that out of the way, we come back to the first confusion matrix. Accuracy for all the predictions is 0.6589 or 65.89%. This may look decent, but it is misleading. The model is identifying streak MM very well, even with only 10 epochs of training. However, its poor performance when it comes to separating perfect MM and near perfect MM is bringing the overall accuracy down. Notice how low the sensitivity and precision scores are for both of the labels. They make the model look almost useless. In short, the model seems to be able to correctly identify streak MM patterns from the rest, whereas it cannot yet tell the difference between perfect MM and near perfect MM. Let's see if this trend continues as the number of epochs for training increases. The trend continues. After 100 epochs, the sensitivity and precision scores for perfect MM and near perfect MM have risen. However, we might as well just guess with our eyes if they're so close to 0.5. Are PerfectMM and Near PerfectMM that similar? If so, can we just combine the two classes? Let's find out by using the same structure but training on only PerfectMM and Near PerfectMM. If they are somewhat noticeably different, like StreakMM is from PerfectMM and Near PerfectMM, they would be easily identifiable by the current model. Accuracy for all the predictions is 0.50056 or 50.056%. Plus, we still see that trend of poor performance in the sensitivity and precision scores. Let's train for more epochs. Accuracy for all the predictions is 0.49972 or 49.972%. And the sensitivity and precision scores have swapped places between the two classes. This may mean that the samples from the two matchmaking algorithms are so similar that the model cannot tell the difference and is just plain guessing. It may be a good idea to combine the two classes for further training of models and call it PerfectFAM. Now that we have PerfectFAM, PerfectMM plus Near PerfectMM, let's see how well a model can distinguish between PerfectFAM and StreakMM. Accuracy for all the predictions is 0.9874 or 98.744%. The sensitivity and precision scores are also very high. This model looks like a reliable model for separating PerfectFAM from StreakMM. Let's train for more epochs. Accuracy for all the predictions is 0.99459 or 99.459%. Higher than before are the sensitivity and precision scores. The model became even better in every aspect. Now let's try training a model with live data in the mix. Accuracy for all the predictions is 0.6686 or 66.86%. However, the sensitivity and precision scores for live data and PerfectFAM show familiar numbers. The model performs poorly when dealing with these two labels and is back to being just as good as guessing, or even worse. Let's up the epochs. After 100 epochs, accuracy for all the predictions is 0.6412 or 64.12%. The other scores seem to have stabilized to some degree. However, if we look at the sensitivity and precision scores for live data, they are both below 0.5, whether it's know first, predict later, or predict first, know later. On the bright side, we can still correctly and consistently separate StreakMM from the rest. We want to know if we can use a model to identify PerfectFAM, live data, and StreakMM. But the first basic NN does not seem to cut it, as the sensitivity and precision scores regarding PerfectFAM and live data are below 0.5. Perhaps we need more than just one layer in the middle, or some slightly more advanced techniques, or all of the above. Let's build a convolutional neural network. We'll call this model First CNN. The purpose of the first CNN is to distinguish which one of the three matchmaking algorithms was used for a record. This is what it looks like, with 3 convolutional layers, 2 pooling layers, and 2 fully connected linear layers. Here's how the first CNN performed, trained for different epochs. After 10 epochs, accuracy for all the predictions is 0.67453 or 67.453%. But the sensitivity and precision scores for live data and PerfectFAM are still not decent. The model still performs poorly when dealing with live data and PerfectFAM. Up with the epochs. Just for the sake of experimenting, the model was trained for 300 epochs, even at the risk of overfitting. After 300 epochs, accuracy for all the predictions is 0.65849 or 65.849%. Sensitivity and precision scores for live data have gone down. We may need some adjustments to the model architecture. So far, the CNNs have been fed the input in a 2D format. What if the input was one-dimensional, and we used one-dimensional convolutional layers? This model will be named CNN1D. This model does not perform extremely well. However, the sensitivity and precision scores for live data and PerfectFam seem to show signs of improvement as they approach the 0.5 mark. What effect would a new kind of layer in the model have on the performance? Since we're dealing with one-dimensional data, would adding an LSTM layer help? The new model will have one LSTM layer between the two fully connected linear layers. One very interesting thing here, when trained for 100 epochs, is that only one score, precision for live data, is below 0.5. This is unlike the previous models, where the scores regarding live data always lagged behind. What does this mean? Classifying records on an individual basis is hard, more challenging than doing so collectively on a group basis. This may be because the subtle differences that different matchmaking algorithms exhibit are shared across all the records, and it would be up to our model to spot these subtler differences. More sophisticated models that require heavier computation may perform better, as we have seen by adding more layers of different kinds. But eventually, the performance of newer models will plateau. The main reason is that any pattern is possible by any matchmaking algorithm, at least theoretically. For this reason, too big of a dataset will result in more samples that are identical or almost identical across two or more classes. This will confuse the model being trained and knock it off the right tracks, while the loss is being minimized. If more than one class shares similar traits, as shown when comparing live data and the perfect family using their collective statistical test metrics, it may mean that they possess numerous similar patterns. This is somewhat proven as Streak M, one that has clear distinctions in its collective statistical test values that separate it from the others, is almost always classifiable by almost every neural network model. In addition, it is also interesting to note that a higher number of epochs will often degrade the performance of a model. More epochs mean that the model being trained will be more exposed to duplicate or near duplicate samples with different labels. This only creates more confusion for the model, forcing it to resort to mere random guessing when it sees a sample in which it finds no distinct and unique features for it to judge on. Before we end, recently I have made some tweaks and adjustments on how the data was prepared and how the model was structured. The trained dataset was made more balanced, meaning equal number of samples per label. The model is still 1D but has 4 convolutional layers, 4 pooling layers, 2 dropout layers, and 2 fully connected bigger linear layers. The test dataset was also made balanced with 10,000 live data samples, 10,000 PerfectFam samples, and 10,000 Streak M samples, so that we have a less complicated confusion matrix without having to worry about the relative sizes of classes. We will call this model as Balanced CNN 1D. After 10 epochs, accuracy for all the predictions is 0.745233 or 74.5233%, higher than before. All sensitivity and precision scores for live data and PerfectFam are above 0.5. For those interested, the Matthews correlation coefficient was 0.2363 regarding all the predictions. Although this model could or should be trained for more epochs, it is the best model we have so far. Let us have some fun. If you feed the model a sample from PerfectFam, know first, it will predict right 64.49% of the time, predict later. If you feed the model a sample for the matchmaking algorithm used, predict first, and the answer it gives is live data, you can trust it to be correct 62.46% of the time, no later. And if the model spits out streak mm in any usage case, well, good luck. Happy grinding, more videos coming soon.